Okay, guys, can you quickly tell me if you can see my share screen? Okay, sounds good. Let me have it. All right, so welcome to the first online lecture of 2021Z. First of all, I'm seeing that around, let me see, 42 of you guys are on, which is not bad. I've already set up a poll, so if you click on polling, you're going to see the poll, right? And basically, I wanted to have your opinion about the weight of the final. As of now, we are sure that we're gonna have the final exam online, unless something dramatically changes or everything gets back to normal, or we all die. So either of the cases. So we're gonna have the final examination in online, and originally it was intended to be 38%. So I would suggest, if you're not comfortable with having an online examination, or it might just add you more stress, or you feel like you've been doing pretty good up to this point, I mean, feel free to voice your concern by polling. And I would hope the number of polls will pass at least half of the class plus one. I guess you guys are 160 in the class, so I hope the final poll number would pass above 80, and that would be sort of democratic polling, I would say. So far, you're 42. So ask your friends to join in and poll in if they are interested. So that's for that. Secondly, I'm recording the lectures. So after, I've already put up the slides as before in Moodle, so you're gonna have access to the slides. So on the first portion of the lecture, we're gonna talk about the final part of pipelining. I'm gonna have a very detailed example on pipelining and the kind of question you're gonna see in your final exam. So that's gonna be pretty close. And after the quick break, we're gonna have the first part of chapter 5, which is cache. All right, so the slides are up. After the class, I'm gonna upload the recorded lectures on YouTube and pass you the link, the same playlist you used to look for. So that's it for that. Thirdly, so somebody's asking where's the poll. Just look at your Zoom. So there is mute, stop video. You're gonna have polling. You're gonna have other things, right? So there is polling there. Click on that. It's gonna pop up. Did you find it? If you are in full screen, perhaps you need to bring your mouth up, and it's kind of just gradually, it's like a curtain, it's going to go down. If you're not in full screen, it's going to be in bottom side. Okay. If anyone wanted to ask questions, just unmute your microphone and ask questions. I remember there was a function for like raising hands, which I don't see it anymore. So you just unmute your microphone and then ask your question. But make sure to mute it again, because it's gonna do an bounce back. So we're gonna have problems with the audio. So that's the second point. You can still find it. Yeah, yeah. Apparently, yeah. Raise hand is still there. Yeah. If I wasn't talking, just feel free to talk. Just unmute your microphone and talk. Thirdly, tomorrow lecture section 1 in the morning, and in the evening you're gonna have lecture 3, section 3 for the lab, and also Wednesday in the morning you're gonna have the what was that, the section 2 of the labs. Okay, so just like before, what you're gonna see is so I'm seeing a chat here. What is it? Are we going to chat in WhatsApp? You can chat here. Yeah, I'm not going to join that group, so feel free to just chat with yourself. Yeah, yeah. All right. Okay, I'm not going to join there then.
Prof, I have a question.
Yeah,
The students were asking that if the weightage is shifted, where would it go? Like in the labs or the midterm or both?
all of them. So far, I mean, by completion of your lab M, which is going to be tomorrow or the day after tomorrow, and then next week lab N, you have accumulated 62% of your final grade. Okay, so that, given the fact that you're going to keep the original weight of 38%. If you decided to change it to 30, which will be determined by the end of this class, or 20 or 10, I just have to amplify that 62% to redistribute for the rest. Okay. So for me, it would be the same. I have to spend the same amount of time to just make a question, and then your TA will gonna spend the same amount of time to grade it. It's just the final outcome would be different. So that's an option for you guys. Everything would be the same so far. So as I mentioned, 62% of the grade of the course you've already accumulated by the end of lab N, which is going to be next week. So the only remaining part would be 38% of your final, right? So about the labs, as I mentioned in my announcement yesterday, so you're going to be given questions now. Instead, you are physically there in the Lassonde labs, and then you are logging into the machine. Just check under the tab section on your Moodle, which you use to find your pre-labs. At each section, section 1, section 3, at this appropriate time, right on your lab test time, um, you're going to find your lab test question. I will be seeing who is downloading those, okay? So other student of the section, please do not download the PDF of the lab. Okay, if you download a PDF of the lab test tomorrow for which you were not belong to, you are entitled to answer that lab. Okay, if you are in section 3, which was tomorrow evening, and you downloaded the file, I'm assuming you are attending the lab. Okay, so distribute this to other students as well who are not attending, because we are 45 for now. So if you think you want to just to have a look at the lab test tomorrow and then don't answer it, you're gonna get 0. Okay, because I can see whoever logged in on Moodle and downloaded the file. So just like before, you're gonna use Web Submit before the lab test. You're going to submit your pre-labs, and then I'm going to open up another folder, which is going to be, instead of pre-M, would be M01 for tomorrow morning, M03 for tomorrow evening, and M02 for Wednesday morning. Okay, and then you're going to submit your lab test, the actual lab test, again by Web Submit. Okay, to its appropriate folder, and then after 1 hour, not 90 minutes, 1 hour, right? I'm going to close the submission for the lab test. So everything would still remains the same. And I'm assuming all of you are already working on your laptop with Icarus, so that shouldn't be an issue for us. Okay? Which section will have the easiest? I'll try my best to make it as uniform as possible. So all three would have the same, um, you know, level of difficulty. Okay? Any other questions? Yeah, somebody was just writing here, I don't want to wait to be distributed, so just voice your poll. There's a polling online. Ask your friends to come join the Zoom and then poll, because we are 47 so far. Okay?
Professor,
Yeah, go ahead.
sorry, I have a question.
Sure.
Uh, I think I joined late. It's about the final exam.
Okay.
Uh, it's out of 38, I guess, or below. But what's going to happen for that?
So have you seen the poll that I set up?
Not
So
really.
if you click on the polling on your Zoom app, there is a, it's either on the top or in the bottom, depending if you're full screen or not. Click on polling, you're gonna see the poll in progress. Can you see it?
No, I'm on my phone and
On your phone?
not.
I'm sure there is a shortcut on your phone. If somebody has accessed the polling via phone, he or she might help your your friend.
Prof, can you make the poll available on Moodle, like a straw poll or something?
I can do that.
Because most people don't like have access to it, and like not everyone is in the session either.
Yeah, I mean, sure, why not? Let me see if I can put the polling there. All right, so in this case, I'm gonna put the polling in Moodle when we have the break, okay, in 1 hour, and I'll put an announcement and give you guys like some hours to just answer. And by the time, if you pass the 50% plus one threshold, which is gonna be around 85 students, so we're gonna decide whatever the population of the class wanted to go with, okay? Can we still submit through Prism SSH? You can submit from anywhere now. It would be just you're not entitled to be in the lab, okay? You just have to submit to the appropriate folder. The easiest way would be just to stay home or stay in wherever you've been working in the past couple of days, and then just use web submit and then drag and drop your files, right? It would be the easiest one. In this case, you don't have to go to university at all.
Question.
Any other questions?
Is the date of the final impacted at all, or is it going to be the same date?
No, I guess by now it would be the same. I mean, we're still a month away from it, and you never know what's going to happen. But so far, everything is fixed. You just, instead of going physically for the exam, everything just stays online. And we were lucky because this course, we could sort of adapt to be online. If we needed other materials or just some physical access to some devices, that would be a problem. But for now, yeah, we're good. And we've already done like 60% of the materials, and then 60% of the grade, and then we are almost done with the lectures, like a couple of more lectures and we are done. So we were kind of lucky. Okay.
Thank you.
Yeah.
Hello, Professor.
Yeah. So let me just yeah. So I'll leave the poll for now, but then we're gonna have another poll in Moodle, unless we pass 80 people right here. We are at 50 now.
Hello.
Yeah.
I wanted to ask for the lab tomorrow. Can we submit through VirtualBox? Are we allowed to do the labs on VirtualBox and then submit through there instead of Icarus?
Which VirtualBox?
The labs tomorrow for the labs.
No, you want to submit it via VirtualBox?
Yeah, through VirtualBox.
What is a VirtualBox? What's your definition?
It's just like we're on the school environment, like we're on the Linux environment, and we're doing the labs through like the school.
Yeah, sure. Let me double check if your lab test is being canceled. Otherwise, everything's fine. Let me see. Yeah. So yeah, lab test would be canceled. So yeah, you can submit anywhere, but just refer to the exam text. I'll provide you the instructions on what folder to submit. Your pre-labs are already open. So if you go to just Google York Web Submit, you're gonna see pre-M folder open for 2021Z, right? If you tomorrow at your specific lab test time, you're gonna see either M01 or M03. And Wednesday morning you're gonna see M02. I'll provide the instructions so you know where to submit. Make sure you submit in the right folder, okay? And another repetition of what I said for those guys who were not here. If you got access to the file of the exam, which wasn't in your section, so you were in section 3, which is tomorrow evening, and you downloaded the question in the morning, I see who had access to the file, okay? If you access the file, you need to answer it in 1 hour. Otherwise, you're going to get 0. All right? So if you are not in that section, do not see the file. That's as easy as possible. Yeah, you can zip the easiest way would be just to zip the file and submit it this time. All right, shall we start it? Any other questions?
Yeah, I have a question. In terms of like the midterm marks was like when we went to see the TA and they updated it, but like when are you gonna update the Moodle?
I updated the grades yesterday. Have you checked it?
No,
I have
I didn't.
updated some grades, so check and feel free to email me. All right.
Okay.
The
All right.
installation of Icarus, just check your Moodle. There are instructions there for month. If you had other questions, let me know. All right. Okay, let's get started because we are running out of time. Okay, where we are now. Okay, if you had questions, just unmute your microphone and talk. All right, but make sure you mute it back. So if you recall, we've been talking about pipelining, and we arrived to the point that we know how to do the forwarding, right? So address basic forwarding hazards, which almost related to data hazards. Now we're going to just shortly talk about the branch hazards, okay? And a couple of slides about branch predictions. And then finally, we're going to have a complete example of pipelining, which you might see in your exam, okay? So what we're going to do here is like, this is an example of branch outcome. In general, so suppose you don't have any optimizations, right? So that's your first operation, first order instruction, right? It's branch equal, and that's the PC line, 40, and then you're gonna have 44, 48, 52, and up to this 72, right? So the outcome of this branch will tell PC program counter to either go to this line, which is 72, right? Or just go sequentially and execute the other instructions after each other, right? So after 40, either we're going to go to 72 or we're going to go to 44. And the reason why we are going to 72 is this is a PC relative addressing, right? So our relative addressing was already 40, right? So 16, which is going to be multiplied by 2 because we are addressing in 8-bit bytes. So if you add these two together, it's going to be 72, right? So that was your relative PC, and that was the target of the branch, right? So it would assume that if branch equal, branch not equal was of x1 and x0 and 16 was taken, you're going to go to 72. If it wasn't, you're going to go to 44, right? Which is the rest of the instructions. Okay, so now we have to decide in the old pipelining, the classic way that we talked in the previous lecture. So instruction fetch, and then you're going to have your ID, then you're going to have your execution, then you're going to have your memory, and then your write back, right? So let's see how we're going to do and how we're going to address a branch hazard, okay? So that's the same question, that's the same problem we've been talking about, right? So we arrived to the point that we are at the branch, right? That was assumed that was a basic block. So in the basic block, we have to decide if we want to go to 44, which is an AND, or we're going to go to 72, right? Or here. Okay? So if we add more hardware, and we notice this feature in previous lecture, that normally in your classical pipelining, you're going to have your ID, you're going to have your execution, you're going to have your mem, and then you're going to have your write back, right? So we are adding more hardware to determine the outcome of the branch from the previous one. That was the if, right? From the previous instruction, instead of instruction fetch at ID. So that would buy us one less stall at least, okay? And if we find it at memory, which we are doing here, because the outcome of the previous one, instead of write back, can be determined at memory, because at the end of the day, when you are in the data path, the outcome of the memory will be written back, right? So at the same time, we can just pass it as a forwarding channel to the instruction fetch, but not even instruction fetch at this point. We're gonna go to ID. So this would buy us one more stall. So instead of 3, we save 1 stall here because we don't wait up to the write back. We're gonna save another stall here because we can anticipate. So this is a sort of an anticipation or prediction.
Professor,
Yeah, go ahead.
I have a question. So in the example given,
Okay.
what is the parallel happening?
The parallel for.
So you're saying for the stalling, for saving some time. In the example given here, where is it happening? Where is it showing that you are saving some?
So this is just a statement of the question. We're going to see it in the next slide. So this is just telling us that we are using more hardware and we are determining the outcome of the branch instead of instruction fetch to ID. And then we're going to see in the next slide what would happen. So in the previous slide, there was another piece of information for us, which was that the branch outcome determined in memory, right? Instead of write back. So instead of write back, which was here, it would be determined here. So we are, instead of putting 3 stalls, you remember in the previous cases, in no optimization, right? When we have these 2 pipeline. Okay. So instruction fetch, ID, mem, execution, write back, right? So if we are going from write back to instruction fetch, that would require 1, 2, 3 stalls, right? Without anything. Now, the information provided to us is giving us the hint that instead of write back, we are determining it in mem. So we can pass it right here, okay? We don't have to wait for the write back. So we can assume 1 fewer stall, okay? On the next slide, it was giving us the hint that, okay, instead of instruction fetch, which is here, we can anticipate it at instruction ID, so 1 more stall can be saved for us. So if we have these 2 optimizations in branch, which we will see how, we're gonna save 2 stalls, okay? But nevertheless, we're gonna use, we need 1 stall in order to just pass the branch if we are using it here, because at this point, no matter what, if we are anticipating that ID, we need to know if we are going here or we are going here at all, right? There are 2 different ways. It's a branch, right? So
I have a question.
Sure.
So the previous slide, the one you were just explaining, when does it go to 72 and when does it go to the next?
So when the outcome of the branch is taken, you're going to go to 16, which is when the outcome of the branch turns out to be not taken, right? It depends on the value of these 2.
Okay.
If you take the branch, so you're going to be here, and normally we just write taken or T, right? If it wasn't taken, you just carry on executing whatever it was. So normally we write NT or not taken, okay? In the example that you're going to see in a few slides, and you're going to see in your final exam, you might be asked to just provide how many stalls we're going to need for such a question, so that in either cases, we might have like some stalls needed, right? Depending on the type of the branch. And you're going to see the example here. So if you go back and put this information on your data path, you're going to, so that's something similar to this. So you see, so this is your sub instruction. That's the instruction after that, because it's coming after that. So you're filling up the pipeline this way, right? So this was the first instruction, that was the second one, and this is the one after that, right? So the output of this branch, while this is in execution mode, right, we can determine by adding more hardware that if the idea stage, which is here, if the idea stage of clock cycle 3 determines that a branch must be taken, it will select 72 and then pass it back to the PC, okay, as the next PC address, right? And that was why we needed a controlled unit here to understand and detect the data hazard. And if necessary, we need to play around with the instruction fetch of the next instruction, right? Why we have a flush here? Flush is just resetting it to 0 or resetting it to a preset instruction address. That's why, because we don't know if this instruction would be executed or the outcome of the branch at line 72, right? So if our branch prediction was wrong, we need to flush the IF, which means that perhaps instead of 44, we're going to go to 72, right? So one of these two. If we were correct, so that would be perfect. We can anticipate the branch at ID, and then we're going to go with the 72 or 44. And that's why you have this IF flush. We're going to see some details about it in a few slides as well. So that's the way it goes.
Sorry to
Sure.
interrupt.
Go.
Yeah, why we need 2 times 2, 16 times 2 to get 72?
Because this is a byte addressing, right? So the address you're seeing, it would be 32 to 64, okay? And each of those bytes are 8 bits. Okay, so you need to provide the full address for that. And the 40 comes from the relative address of PC, which was here. So at this point, PC was 40. That's the program counter at the point of the branch. So if you remember in chapter 2, we were talking about the way we can extend the size of the PC, because some of the modern applications are branching far away. And this is a conditional branch because we are bounded by a condition of checking these two. If you are using a jump or other type of unconditional branch, or in high level, you can think about as move to, right? Or while true. While true is going to be, or sort of an unconditional branch if everything is true all the time, right? So in that case, we needed something larger to contain the address of the branch. Suppose you are branching from address 40 out of a sudden to just 400,000, okay? That this is a very large program and you're jumping here and there. So that's why we are using a PC relative addressing. So you're going to add the address of PC plus this byte addressing of the outcome of the branch, which is like in this case 16. In this case, you're going to be able to just branch up to 2 to the raise of 18. You can again refer to chapter 2 to see the details of why we can branch up to this point. But yeah, that's the way we address the branching here. All right. So at the IDE stage, if the clock cycle determines that we're going to go take a branch, it's going to select 72. Otherwise, and zero the instructions and flush the PC. Now, in the next cycle, at cycle 4, so now you see this branch has moved here, okay? You remember at the best case, we had 2 optimizations. One, the case that we are determining the outcome of the memory as the final result while it's getting written back. So one stall we could save, and also at the same time we were anticipating the outcome of a branch at ID. So that's why nevertheless we needed 1 bubble or 1 stall instead of 3, and that's the stall here for us. So this clock cycle 4, right, shows that the instruction at location 72, that was at 72, right, is being fetched, and a single bubble, right, and the knob we just talked about would be used only because the branch was taken, right? So we can just put T here because we took the branch. If it didn't take the branch, look what would have happened. So if it didn't take the branch, it would have been here. We would have executed line 44 at PC, right? It would have been an AND instead of this one, right? So we took the branch and the PC is at 72. All right. So how are we going to anticipate this in ID? There are so many techniques, and some of them are more in detail and more advanced. So in this course, we are just talking about some of the techniques, very, very high level. And whatever we discuss would be only part of your exam, because some of the portion of the slides that I don't teach, which you don't see in your slides, won't be in your exam. So that's why I uploaded the slides here. So just feel free to just read those slides that we uploaded. So the overall technique for predicting the outcome of that branch is called branch prediction, right? One method for that would be a dynamic branch prediction. In more recent, CPUs or processors, we have dynamic predictions, right? And there is a module or a hardware called a branch prediction buffer, which keeps the branch history. Suppose you're running a loop, right? The loop will run 200 times, 1,000 times, right? And you're at the iteration number 500. So say 500 of the iteration of the loop still remain, right? So that branch prediction buffer provides us with a branch history table, right? Like it's going to just save at iteration number 1, we took the branch. At iteration number 12, we didn't take the branch, and so on and so forth, right? And with having this data and so many other different techniques, and at this point, it's going to be like processing this data, right? This branch history. Are we going to take the majority of the previous history? Like if the previous history shows us 90% of the time we took the branch, right? And 10% of the time it was not taken, okay? So logic might say, okay, 90% of the time, this branch, this code behaves that you did not, you took the branch, right? So it makes sense if you carry on taking the branch. This is one way that you can dynamically use the branch history table to predict the outcome of the branch for that next ID stage, right? Other techniques would be just to use a machine learning model on the fly, which is much more complicated, or other statistical method, or instead of a dynamic branch prediction, just use a static one. You always take it, or you always not take it, or with a probability of 10%, you not take it all the time, and then you 90% of the time you take it. So these have their own pros and cons, and we're going to talk about some of them here. Okay. So we had two slides, the same thing. So one of the ways to have a dynamic branch prediction is just by using a memory called as a predictor, right? You can allocate one bit or certain bit as your bit predictor, and it just saves you what you've been doing before. For instance, if you were doing a taken branch, if you took a branch, you're going to set it, keep it to 0, right? That bit. As long as you made a mistake and you took a branch which you shouldn't have and it was not taken, you might have to set it back to 1. Okay. Now, as long as this is 1, you're going to carry on doing the same, which is not taken again, and you're going to run into another problem, and you're going to see, oh, this bit tells me it's 1, so I should remain in my previous path, which was not taken. Now it turned out I was wrong, so I have to pay the price. I have to flush the instruction fetch and then put it back again to 0, and then I go back to the taken route. So you see, by having a 1-bit predictor, it's going to give us some hint that, okay, in the past you've been doing not taken, or you've been doing taking, so carry on doing as long as you don't have any branch prediction hazard. Okay, the first time you mispredict, you're going to set it back, and then you're going to change route. So let's see what's the pros and cons of having a 1-bit predictor. Assuming you have a loop branch, right? So let me see. Do you still see my screen? Okay. So now, assuming that you have a branch that branches 9 times in a row, okay? Yeah. Okay. 9 times in a row, and then it's not taken once. So it's gonna just, you're in a loop, right? And inside the loop, at the end, 9 out of 10 is gonna take the branch. I'm gonna just say 90%. And then 10% of the time it's gonna do a not taken, right? Okay. So what's the prediction accuracy for this branch, assuming the prediction bit for this branch remains in the prediction buffer? Does anyone have any idea? Feel free to unmute and talk. Any ideas? Are you there? Not sure? No idea? Okay. Okay. So 8 out of 9. That's almost true. So so your friend is confused. So assume that, okay, you are using a one bit branch predictor, and you have a loop which will be run for how many times, whatever it is, it's not important. But 9 times in a row, you're gonna branch, and then there is a not taken, so no branch at all. Okay. So what's the prediction bit for this branch name? So you can, so your friend was mentioning 8 out of 9, almost true, except the last or the first one, whichever he misses. So in a steady state branch, right, the branch behavior would be branching, predicting the true branches correctly up to the point that you're going to have your first misprediction, okay, which is going to be every 1 out of 10, right? So 9 times okay, and then 1 time not taken. So that's your 90% there. However, you're going to have 2 incorrect, so just 1 because of this, and the other one is flipping at in the last one, right, for the exiting branch. So we're going to have 2 mispredictions. The misprediction on the first iteration, because the bit has been flipped, we've been coming here from another block, right? It was a basic block with no branches. We entered this, right? And we started to branch, either go to taken or not taken, right? So this is one misprediction. We needed to set this 1 bit predictor, and then every 9 out of 10 we're gonna have 1 not taken, which is a 1 prediction. Okay, could be the last one. So that's why instead of 90%, we're gonna have 80% accuracy in this branch predictor using only 1 bit, because you come from a basic block with a branch predictor set as 0, for instance. You hit to the point that you need to branch, so that's your, and a branch would tell you either to take the branch or not taken, right? So like 90%, 10%. So this is one mistake, and every now and then when you are switching from 90% to 10%, you're gonna have another one. So overall, you're gonna have 80% accuracy for this. All right? Questions on this? Yeah, you're still talking about the polls.
I have a question. So
Yeah.
I understand. So for the example that you gave, you're saying that there's a basic block, and then we then choose whether it's taken or not taken.
Exactly.
90% is going to be taken, and 10% is not going to be taken.
So we were in a basic block, and now we are in a sort of a branch in a sort of a loop or a condition, right? So we used to be in a basic block, but now we are talking on this block, which is either assume it as an if and else segment. If this one was greater than that, do this. Or if it was a while loop, right? Or full loop. So before entering that, we're going to pay a price of one misprediction, because before that we were just going sequentially with the program counter, right? That was our program counter.
Yeah.
And then we're going sequentially, and then out of a sudden from the basic block we entered the branch. Okay, so we pay one mistake for our base, because this one was telling us, okay, go ahead, go just sequential, and then out of a sudden we entered in this. Okay, and then exiting this will be either taken or not taken. So another 10%, because 90% of the time we're going to take it, and 1% or 10% of the time, 1 out of 10, we're going to not take it, right? So that was why instead of 90%, we're going to have 80%. And this is because we had only one bit predictor, because this is either getting set to 0 or 1, right? So now somebody might say, okay, so we were using only one bit predictor. What would have happened? You see, so that was the outer side before entering the basic block, and then you're going to be in your block of the branch, and then this itself will have its own 10% misprediction, and then you're going to come up with 20% overall, 2 out of 10, one because of the taken and not taken, and one because of the first one. Okay, so one might say, okay, this is just because we are using one bit predictor. If we have enough of hardware, if we have enough of space, why not allocating more bits to this? Can we just allocate 2 more bits, right? Make it a 2-bit predictor. Let's see what's going to happen. On that case, we're going to have a similar paradigm like this. Okay, now it's pretty easy. Just you're going to understand the logic pretty easy. So by using a 2-bit predictor rather than one, a branch that strongly favors taken or not taken, as many branches do, right? Because sometimes we are in a basic block, and then we entered in a loop. We need to loop over it for 1,000 times, right? So, and 1,000 times we need to compute something, like add this to that and multiply this to that, and then finally after the 1,000th time, perhaps we're going to exit, right? Who knows? It might be the case that after the 5th iteration we might exit. That's why we need to predict the outcome. But in general, in a 2-bit predictor or more bit predictors favors staying at wherever they were. It's like some inertia, right? You want to prefer to stay at whatever state you used to be. Okay, so let's see how that works here. So let's start from here. Assume we start from here. Okay, so we are here, and we are at the point that we predict the outcome of a branch. Okay, either we have to not take the branch or take the branch. Okay, so now the predict is taken, right? So we predicted we should take the branch, and it turned out to be that, oh, that was true. Okay, it was taken. So the prediction was taken, and the actual branch turned out to be at the ID stage to be taken. So we're going to stay here because the prediction was taken. We took the branch actually, so we're going to stay here. So all so far so good. Okay, we remain here, and if it was 1,000 times, we're going to just carry on doing taken. We predict taken, and actually it turned out to be taken, and we stay here. All right, now out of a sudden, either we hit the last one or a condition inside that for loop, right, didn't meet, something changed, and your iterator went out of bound, and then you understand, oh, you were carry on predicting taken, right? We thought the prediction outcome would be taken, but the outcome turned out to be not taken. We pay the price because we mispredict. Okay, so having a 2-bit predictor allows us to compensate this again and stay in our previous lane. It's not a one-bit predictor that right away we're going to set it otherwise, and when we go to the other line, and the other line would be what? Not taken. Okay, but since we have two predictor, we are affording twice, right, to mispredict. So that's the essence of it actually. So on the first one, we are not right. The outcome of the branch we predicted to be taken, it turned out to be not taken, but we are still here. So we come here, we are still in the state of the prediction taken. Although we made a mistake, we stay in our lane. Okay, that's why we come here, and here still tells us to be taken, right, on the upper side. If we come here, it would be a not taken. Okay, so although we were wrong on the first choice, from the predict taken, the outcome was not taken, we are still here. We carry on doing the prediction taken. So now the next one, we still in the mode of take the branch. We predict still take the branch, and it turned out to be true, right? If it turned out to be true, we're going to come back to the safer land again here, still in a taken land, but now we can afford again to lose one, right, prediction. However, if we arrive here, so we already mispredicted once because we told the program counter that, okay, take the branch, and it turned out at ID that it was misprediction, and we were here. If we do it again another times, that would bring us here. So now, because we are avoiding on the second one, we can't help it but to change the prediction outcome of the branch. You have to set it, right? You have to set both of the bits, and now we are in a not taken land. This will just tell us, oh, apparently we are keep making mistakes, so this is the second time that we did a mistake in a row, so perhaps it's time to change our course of prediction, right? So now instead of prediction taken, now we are hearing prediction not taken. Okay, so here, if at the first if at the first state of the prediction not taken, we took the branch again, so that's going to be the third misprediction in a row, we come back to the predict taken, right? But if it turns out that at prediction not taken, we didn't take it again, so it turns out that apparently we are in this path now. So the lane would be this. So another not taken for the prediction would bring us here. And that's going to be exactly the opposite of the first start, right? Perhaps we arrive here. Or in the worst case scenario, when we are having a 2-bit predictor, we arrive in this no man's land of just going from this one, and it's going to just give us prediction errors one after another. So all the misprediction. And one might think, oh, in this case, we could have added more bits here, right? 3-bit predictor, 4-bit predictor. And indeed, that could be the case because this just makes this prediction paradigm more complex, but give us some slack to just make some mispredictions while remaining in the same lane, right? So that's another way to predict the branch. Any questions on this?
I have a question.
Hmm.
So when we were in taken in the beginning,
Right.
we have the input that we have, or the thing that we have is 100, right?
Right.
So when we had one, it went back to taken. It looped back to itself.
Yeah, because we predicted to take the branch, and it turned out at ID stage that we had to take the branch, right? So we were right. So that's a correctly predicted branch. So we stay at where we were.
Is the prediction related to the input, whether it's 1 or 0? So is it, did we predict that it was taken because it was 1, or that's not related?
Yeah. I mean, so assume that this could be like 0 for the taken, or 1 for the not taken, or the other way around. Like either of the cases you can assume, right? But having this 2-bit predictor gives us some slack just not to change lane by the first misprediction. You see, by the first misprediction, we were still in the lane of taken. Or if we were here, by the first misprediction, we are still in the lane of not taken, right? It gives us one more chance to come back to the correctly predicted lane. Or if it turns out that the second misprediction happens either from here to here or either from here to here, that means that we need to change a lane. Apparently the loop, either the behavior of the loop is changing, or it's just a random random loop that just keeps changing, right? And then we keep paying the price of misprediction, because at the end of the day we are trying to save that one more stall from the memory, right, to the ID. That was the instruction, fetch and ID, right? We are trying to save this to come back here and just put one stall. And this requires sort of a prediction, either dynamically or statically, right? So we are and assume that your program is running like 10 million cycles, right? Just in that loop. Just by that predictor, you're going to save, you might be able to save 1 million cycles, and which is a lot of power efficiency, right? And it is very important for programmers, for designers, to just save as much as they can in their hardware. All right?
Okay, and I have another question.
Hmm.
So once we have two not takens, we
Right.
lower part on the bottom right, predict not taken. And then once we reach there, do we need another not taken?
So
Two not taken.
we started from here, we mispredicted. So from prediction taken, it turned out to be not taken, so we are here. If
Yeah.
we another time mispredicted in a row, so that would be another not taken, and now we need to shift the lane, right? Now we are in the not taken lane. Okay, now we are here. In this case, now the logic of the predictor tells us now you're in a not taken lane. So you don't have to take the branch. So not take it.
Okay.
If
So
it turned out to be true, so that's actually a not taken of the not taken prediction, and we're gonna arrive here. If that was misprediction, we're gonna come back to this.
okay.
Yep. Any other questions? Okay. All right. Yep.
But the question is on 2 slides before this, for the question that is the 90% and 10%.
This one? Yeah.
Yeah. You said everything you were explaining, except when you said it becomes 80%. So
Yeah.
I understand that in the beginning we have 1%, 10%, or 1 out of 10. That
So 1 out of 10 would be inside that branch, right? So assuming this is your program that is running. So that was sequentially, right? No loops. We call this basic block, if you recall. A basic block is a block without any branch conditions, right? You sequentially do and whatever it was. And you reach to the point that is not a basic block anymore, and then you are in a loop condition or any other condition. So when you are using a one-bit predictor, this would have been set either to 0 or 1, right? It's like go whatever it was. And then out of a sudden you enter the branch, and now you have to decide which way you go. Either you're going to enter the branch or just you exit the branch. So that's just one misprediction right away before you start. And then the branch itself has 10% misprediction because not taken is 1 out of 9 in a row. So 10% you're gonna have here, and then assuming the whole thing was running million times, so asymptotically we're gonna say that okay, 10% we're gonna lose here, and then 10% we're gonna lose for the. So actually, it's just like the last and first instructions, right?
Yeah, that makes sense.
Okay, sounds
But
good.
do we need to really understand that why is it first and last, or do we just need to know that the misprediction will happen first and last always?
Not really. I mean, these questions are pretty easy to analyze. I'm not going to give you like analysis questions, but you're going to use this information to understand how you're going to solve the example that you're going to see right now. You're going to be given an example with table, and then you're going to solve it, which I'll show you right now. All right. So actually, this is the example. So this might be a question that you're going to see in your exam. So I'm going to give you a high-level code, right? C, C++, Java, which is pretty easy, like a do while. So what you're going to have is like you're going to increment, right? Two increment 1 and increment 2, two vectors or matrices or anything in high level, right? And then you're going to have the I++, and then you're going to check while I wasn't n up to the point, you're going to carry on doing this, right? So, and then I'll give you the RISC-V as well, or I might ask you to write a RISC-V for this, which is pretty easy. You're going to have to just load the first one, right? And load the second one, which is this one. And then you're going to add first one with one of them and add the second one with another one, right? So that's the first fourth instruction. And then the outcome of the add of the first one with increment 1 and then base B with increment 2 would be added together. And you're going to come up with the final one, which is the store. And then you're going to add I, the incrementor I, and then you're going to decide. We're going to go on the branch if not equal of the I and 10. And I'm going to give you in at which registers these instructions have been initialized. And then so the outcome of the branch either tells you to exit the branch or come back to L1 where you carry on doing the for loop. Okay, so that would be a pretty easy start. Then I'm going to give you this table. So branch was not taken the constitution. So yeah, and then I'm going to give you such table, right? You're going to fill up the information here. Either you translate it from here or it was given to you, and this table is already predefined for you. So now your job would be to draw the pipeline scheme by marking in red the data hazards, right? So you just have to understand, okay, now let's parse it together here. So now you're going to see that right after you load, okay, so, and remember, the first part of the question is always no optimization. So that's why we have without any optimization, assuming you have the classic pipeline of 5 and then no optimizations in there, right? Instruction fetch, ID, mem, x, and write back, right? So it makes sense when you have to wait up to write back to fetch the next instruction, right? That would require 3 stalls because there are no optimizations, no forwarding, no branch predictions, no fancy stuff, no reordering. So that's the first part of the question. No optimization. First of all, find the hazards. Let's see which of those, and you can easily scheme the code and see, okay, $2, which was for this one perhaps, is getting used to add I while it's being loaded, right? It's getting, so actually this should have been LD, but assume I'll fix it later. So this LW is LD. So this load of the register number 2 is getting added with the increment 1, right? So these two. So now you can easily see, oh, after I need to wait to write back $2 in order to be able to execute it in the next instruction. I need to wait up to the ID stage of that. That requires 1, 2, 3 stalls so that this one becomes here, okay? And then you have to write the type of hazard, which is a read after write. If you can just write $2 and data hazard, right? This read after write wouldn't be necessary, but it's just pretty easy to understand. So it's the read after write. You are reading $2 after it's getting written, right? So that's why the value you read is not correct. So suppose that was this value, right, which was 7, and on the next instruction you were reading 7. However, 2 instructions later this turned to be 10. So now you have a value for $2 as 7, but the actual value is 10, right? And this is called a read after write. This is a pretty classic data hazard. You're reading after it's getting written. So you're gonna write, so up to this point, we are at line 2. Up to this point, is there any questions? All good? Write a yes and no, so I see. Okay. COVID-19 is yes. Yeah, you should be negative all the time.
I have a small question.
Yeah.
So for the operation, we're circling the ID. And then for storing it back to $2, we're doing the write back.
Right.
Okay. And for the write after read after write, shouldn't it? Oh, I don't understand why is it read after write, not write after read. Although we are writing it, and then I don't know if we read it or not.
No, we are actually reading it after it's getting written, right?
Written in the above line or on the same line?
So let's just come back here. Let's just have it this way. So assuming this is, let me just erase this. So assuming this is your pipeline, right? These are your registers, each of the instructions. So the first instruction is at this point, okay? I'm gonna just write PC 4, okay? Now, because we don't have any forwarding, we have anything, we have nothing, right? So it's gonna write back the value of $2 to memory. I'm sorry, this is X and this is memory. Right? Finally, it's gonna write it back here. But we have to wait up to this stage. Okay. The PC plus 8, which is the next instruction, is trying to fetch the instruction, decode, and initialize the values, right? However, it cannot because it has to wait for this instruction to get written back, right? If it reads something up to this point, it had access to whatever it was at this point when this PC plus 4 was passing through the pipeline, right? If it reads something, it's going to get written after that. Okay? So that's why the classical problem would be a read after write. Okay? The read would be something that has been written after that. Okay?
Okay, but when you say type
We,
of
we
results,
also
you mean
we can
that
also have in some situations, let me just clarify this. In some situations, we might have write after write or write after read. So these are other hazards. But you don't have to classify them correctly in this course because you haven't been taught. But you can just, even if you're not comfortable with read after write, you can just write data hazard $2, okay? Yeah, but do know that we have 3 classes: read after write, write after read, write after write. In databases also, it's very important. Okay. All good?
yeah, all good, thank you.
Okay. So now we understand that, okay, for the first 2-1, we loaded and we were reading something after it's getting written. So it's a read after write. Okay, so that's why it's not correct. We need to wait and put certain stalls. But at this point, we just have to analyze and by an arrow, right, in red, we need to show the hazards. The same thing goes for the instructions 3rd and 4, because we are exactly doing the same thing. Instead of just doing this with this, we're gonna do this with this one, right? So base 1 loaded plus this, one read after write. Now we are doing the same thing for 3. We load this and then we add this with the increment 2, right? The same thing would happen here. Again, you're gonna have this loaded, and then you're gonna have this ID, okay? Does this mean the ID for the second instruction must happen after? Yes, exactly. And that's why we need to have stalls here, right? But at this point, we just have to mention the data hazards. We don't have any optimizations, so no forwarding happens here. And there is no branches at this point, so there is no branch prediction available. So that's the classical way of 3 stalls in a 5-stage pipeline, right? We have instruction fetch, instruction ID, execution, and memory and write back, right? So we have to wait up to the write back of this to pass from instruction fetch to ID, because at ID, if you recall, we decode the instruction that we fetch, right? We know what the instruction is. It's this instruction. We know what to fetch, but we don't know what to decode because we don't know what the value of $2 is. If you recall, in instruction decode, we are doing 2 things. Decode the instruction we fetch. So from binary, we're going to decode it. I'm sorry, yeah, we're going to decode it to put it in the control flow. It should be decoded. And then we need to initialize the values of those registers, right, in a data path. So we don't know what that is. We just know it's $2, but I don't have access to the most up-to-date value of $2. That's why it's going to be a read after write. Whatever I do is going to be a read after write, unless I wait 3 stalls, and then I'll have the most up-to-date one. Okay.
I have a question.
Sure.
By saying we need to wait 3 stalls is as if we're saying we need to add 3 bubbles. 3.
Exactly. Yeah. So bubbles, stalls, no operation, all the same. So
Do we add 3 rows of bubbles, or do we add 1 row of
at this point, no. We just have to mention because it would be messy, right? If you put it here, you just have to mention the type of hazard. There is another part of the question that would ask you how many stalls it needs. Okay. Other than that, it would be just a long. So instead of 12, we would have just gone up to like to 30, 35, and it would be a messy diagram, right? But yeah, later on, you're going to decide based on the optimization available how many stalls it needs to clear this issue, right? From write back to ID now. If I put 3 at this point, I'm going to surpass and I'm going to be fine, because you see, I'm always going forward, right? I can't go backward. All right. Yeah, go.
Question asked to do it. Just so that I understand. Do you put 3 rows of bubbles, or do you put 1 row with 3 columns of bubbles?
It depends on where we are looking at, right? Actually, it makes sense to put 3 bubbles, so that would be like 3 rows of bubbles, or 3 no, because actually when we put bubbles or no operation, what does that mean? One stage is doing nothing, and then you pass, it's going to go here, and then the next stage is doing nothing, and then you're going to pass, you're here, another stage is doing nothing, right? No operation, no operation, no operation, right? It's as if we have 3 rows of nothing, no operation, right? So that would be, instead of initializing this at C6, we are initializing at C9, for instance. Okay, is it clear?
Yeah, it is clear. Thank you. And I just have one more thing. I know I'm asking too many questions.
No, sure, go ahead.
But I think now I understand why it's read after write. It's because we are reading ID before we are writing WB in the line above it. Right?
Exactly. Yeah, that's right. That's right. That's completely true. All right. So the first issue for the first happens on the second one, right? Because we have 2 base A and base B. So these are almost identical, except the fact that it's read after write of $2, but then here we're gonna have a read after write of $3. You see here $3, it's been used and it's been loaded, right? So we are up to this point now. Now you see we are here, but not only we have read after write of $2 and 3 because of these increments. Now we are adding their output of their increment together, right? This one plus is in increment, let's call it A, and then this one plus increment 2 plus B. Now we are plussing A and B, so itself, this one, and the output would be at 5, itself is going to have some issues again, because this read after write of the second one still holds, because now the fifth instruction, when it's issued and decoded, we don't have the write back of the $3 ready. Also, it's at the same cycle that the write back of $2 happens, right? So in a way, because we don't have any optimizations in our pipeline for now, in a way, it has a read after write of both of them, right? So that's why you need to write read after write $3, read after write $2 again. So now we are up to here. So we have detected 3 hazards now, 3 data hazards, all in red. Read after write $2, $3, and both of them because of the add. Now we arrive to the point that, okay, now we added A and B, it's time to store it, right? We want to use it later on. So the store, again, stores $5, for which we don't know the value of $5 is, because we were adding it to this and we are stuck in the previous one. So the store is still right at this line, requires the write back of the add. So now we're gonna have a read after write of $5. Okay. All right. So we arrive up to here. We have detected 4 data hazards, and at the one before the last one, the penultimate instruction count, we're gonna have the add I of $4 and 4, which is actually resembling this I++. Okay, the I++ itself doesn't do anything, doesn't have any hazards, because no matter what happens in this line, we are doing I++, right? It was 55 and it's gonna go to 56. Okay, so this line itself doesn't have any issues. That's why it's clear. The issue comes at the final line, where we are determining, am I going to go back to the loop, or am I just going to exit the loop and carry on doing the next instructions, right? I was something doing here, and then it's a loop. I'm looping here, but now I have to understand if I'm going to exit the loop or I'm going to just go back to the loop. Okay, if I have to branch, if I have to take the branch or go to L1, or not take the branch and then just leave the loop. Okay, and that determines of the outcome of $4 and $7. I know what $7 is. It has been given in the question, and you can basically see it here. But because of the increment, I don't know what I is. Okay, I mean, nowadays in advanced compilers, we sort of detect there are some optimizations in iterations that we can determine the outcome of this, but this is assumed as a very classical no optimization pipeline. So at this point, when you are before the write back, you never know what's going to be the value of $4, which was the incremented I, right? So you don't know if the outcome is going to tell you to go L1 or just to stay and or just exit the loop, right? That's why now we're going to have a read after write for the value of $4 itself. Okay, and this is not a steal, this is not a branch hazard, because this is still a data hazard. We are trying to compare 2 values for which one of them is not available. Okay, even if we so now we reached the last line, and the question statement asks us to write in blue the control hazards. Okay, so now up to this point, all of the hazards were related to data, because the data wasn't available for us. It was a read after write. But at this point, I remember in branches, nevertheless, we can because in branch instructions, if you remember in data path, we didn't have to wait up to the write back anyways, even without optimization. So at mem, we could have had the results, right? However, there are no branch optimizations, so we have to wait again 3 stalls, because we are initializing at if. Instruction fetch, what does that mean? Instruction fetch needs to know which instruction to fetch. If I don't know if I'm going to go to L1 or the remaining instructions, I have to wait. I have to wait to see what the outcome of the branch is. And it's categorized as a control hazard, right? We show it in red. It's a control, and mem to f, if, right? So this is the first portion of the question you might get asked. From now on, we're going to gradually give you some optimizations, some branch predictions, some forwarding, or maybe reordering, and then you're going to apply that in your question statement. Let me just finish with the first part, and then we're going to have a quick break. Okay, so finally it turned out to be like this, okay, in a more zoomed way. So read after write $2 for this one, the load and the increment of the $3, right? That was this one. Then you wanted to AND these two, so both of them were not available. So from this arrow and this arrow comes here, right? Then you're going to have a read after write of $5 because you're storing it. The value of $5 is not available. The increment itself doesn't raise any issues. But after that, when we are trying to determine, to compare these two, we don't know what the values are. Again, another read after write. And then finally, when we want to run the control for deciding if we are exiting the branch, by exiting branch, that would be like the next instruction here, right? Either I'm exiting the branch or I'm just going to go back to L1. That's why I have a control hazard. Okay, so that was a summary of what we did so far. So normally at the end of each portion, you're going to be asked to write. You don't have to write this. That was the question of your friend, but in hindsight, that would be like this. Okay, if you were to write the full pipeline, now instead of 12, right, starting from C1, cycle 1 up to cycle 12, because of these stalls, 3 stall, 3 stall, 3 stall, 3 stall, 3 stall, 3 stall, now we would have gone to 30. Okay, so this you will be given, and then this part you have to fill yourself. The first portion of the question, no optimization, so you have to write either, you can write it either here, the control hazard, because it's at the end of the loop, or the start of the loop. Either way would be fine. Write this 3 for the loop, and this 3 for the read after write $2, $3, $5, and then that was $2 and 3, and this is $5, and then this is the comparison of $4 and $7, right? And this is either here, the control, or here. All right, so you sum them up, you're going to have 3, 3, 3, 3, 3, 3, or 18 stalls. Okay, your pipeline was 12 without any stalls. That's why if you add them up, it's going to be 30, right? That's why you're going to have a C1 up to C30. The other method to understand this is, normally your pipeline is 5-stage pipeline, right? So no matter what you do, you're going to pay the price of the 5-stage pipeline. But as you recall in the previous lecture, closing the pipeline when it's completely full, closing the pipeline itself requires 4 more stalls, right? Look at here. No matter if you are having any stalls, how many instructions you had? 1, 2, 3, 4, 5, 6, 7, 8, right? You had 8 instructions. So you had to put 5 cycles for the first instruction, right? So one might say, okay, so each of them takes 5 cycles and I have 8 instructions. Why it doesn't finish at the cycle number 8? Because that would finish the first portion of the pipeline, and then you're so before here you're filling up your pipeline, and this is like you're winding down, because there are 4 more stages that should be completed. That's why when you have n instructions, right, normally without any pipeline, without any installs, you're going to have n4 as your cycles, which is this. Okay, if you are adding stalls, here, if you're adding installs here, still you have your 8 instructions, right? You had your that plus 4 of winding down the pipeline, which is this. That's your 4, right? Because no matter what, the final instruction should finish its course of execution, right? And then why we arrive at C30 instead of 12? Because we had 18 stalls. So you can simply compute it as not total number of stalls as your number of instruction plus 4 plus number of stalls. Okay, does that make sense? Yes or no?
I have a question for the last second instruction. Why we don't have the store for the address 4?
4? Where is 4?
with the I++.
I++ doesn't require any installs. That's why this line doesn't have any install, right? This line.
After we store the data from the
Here?
address 5 to address 4, then we use the 3.
Yeah.
This
so,
one.
Yeah, okay.
Yeah,
I'll answer you right
write.
now. Okay, I'll answer you right now. So there is another question that asks why we have 3 stalls at the beginning. That's the control hazard, right? We put it here. Either we can put the control hazard at the beginning of the loop, or you could have just put it here. Because the next instruction after this, you're going to put these 3 stalls. So you could have put it here. Either way, that would be fine. So that's that. And coming back to your question, this line, so that was your question. This store line is depending on the output of what? The output of both $3. And so this line is dependent on the output of $5. $5 is getting added, right, from $2 and 3. So still that's the same old read after write $5. Okay. Okay. How did you get number of stalls? You just have to add them up, right? So 3 stalls for this, 3 stalls for this, 3 stalls for this, 3 for this, 3 for this, and 3 for this. No optimizations. You just add them up. It's going to be 18. Okay. And in a sense, is it because no previous instruction write to $4, so it doesn't have? Yeah, that's right. That's right. Because $4 is just independent from the rest. It's just I plus plus whatever I it was, we're gonna plus it. No instructions was dependent on it. But after that, the branch comparison depends on $4, right? That's why we have 3 stalls here for comparing the branch, and the outcome of a branch comes here, the stalls. That's why the outcome of a branch is in control hazard in blue. That's the control hazard. But this one is because of these 2. Okay. Questions? Any other questions? Okay, so guys, let's have a 10-minute break, and we start in 10 minutes. By the way, I'm seeing that the polls arrived to 77. Okay, if we pass 85, I assume the polls are complete. Okay, so ask your friends if they want to join and poll right now. If you don't pass 85, I have to repost the poll later on in Moodle. Okay, we'll decide in an hour. Okay. How do you access the poll? There is either, if you're in full screen, you're going to see a polling on top. It's going to just come down as a curtain. Or if you're not in full screen, it's going to be in bottom side. How's the poll at 77 if you're... Yeah, people just come and poll and gone, right? These online classes. They're having fun now. Election fraud, yeah. Who knows? Okay. See you guys in 8-9 minutes. We start at 7:40. Okay. Okay, so guys, let's try this. Can you submit your poll twice or not? It should be only giving you the access to poll once, right? Yeah. Yeah, that should be the case. So when you reconnect, you can poll again. Oh, I see. So in that case, it's gonna be a crooked poll. I'm not sure if Moodle has polling. I should double check. Oh, I see. Elsewhere. Because I'm seeing like 96 people voted. So yeah, it does seem a little bit fishy because you're 47 in class, assuming like 20, 30 people join and left, still they won't be reaching to 96. So can anyone try and then log out and then come back and do another poll? I want to see if it's gonna. Yeah, thanks. Oh, you revoted? Hmm. Yeah, actually, I'm seeing that. Yeah, it went up from 96 to 99 now. Yeah, so apparently people have voted twice. That's a shame. Okay. Anyhow, I have to set up another poll then and post it in Moodle because this is clearly the vote of your 46 people, not the class. Okay, I'm just gonna end the poll then at 101 now. Yeah, let me see. Yeah. That was pretty close from no changes to so almost the same people voted for original weight, which is 38%, or make it 10%. So like two either extremes. I was hoping to get either 38 or 30, but like they are somewhere in the middle of 10% and 38%. So I think you need to think about it more when you do your polling, submit your polling. I'll post a link after the class so everyone must poll. Okay, then we can have a better understanding. Yeah, 20% might be. But since you were 47 people tonight, you were not 50% plus one, so it's not still the majority, right? The majority hasn't voted. So I want to hear from all of you, at least a good majority, like 60, 70%. All right, we'll do that after the class. I'll post another announcement on Moodle, and then you're gonna have a chance to poll. Let's just continue. A student asked his. So Eric was not sure where to ask questions. So you're gonna keep asking the questions just before. You can email me. You can email your TAs. You can put up your questions on forum. Your friends or even me might be able to answer you. Also, so we're gonna have two more lectures. So we're gonna continue having it online here for TAs office hours on all three sections on Friday. I'm gonna put up individual Zooms, okay, and share them to you. So I'll ask the TAs to be online at their time. So you're gonna have the same time to just ask questions, the same 1 hour for each of the sections. So nothing really changes. It's just a matter of being, everything is done online, whereas physically, right? And the other thing that changes is the fact that you're submitting your lab, the remaining two lab via web submit. So just instead of 90 minutes, you're gonna have 60 minutes, and then you can just use web submit and do it on your laptop. So nothing really changes. Okay, yeah, no problem. All right, so let's continue. Let's finish chapter 4 at least. Oh, by the way, I'm recording a lecture, so I'm gonna put it up in YouTube in the same playlist and share you the link. If somebody missed the lecture today, they have the option to have a look at it again. All right, so we arrived to the point that the first portion of the question was asking us to analyze the number of stalls. No, the labs would be as difficult as before, so I guess so far they were pretty easy, right? Okay, so the first, yeah, I'm just crisscrossing on that. Here, okay. Oh, now I can get rid of this. I can't erase it. Interesting. Wow. Okay. Wow. It's there. It's a permanent. Wow, that's such a glitch. Can you see this yellow, these red lines here? That's such a glitch. Wow. So my monitor has been perhaps forever damaged by my pen. Yeah, apparently I use a permanent one. This is epic. Okay, yeah, that's so. Let me see if I can. Wow. Um, how can I erase it now? The result of the poll, well, invalid because you were 47 and we had 102 polls. Okay, I'll send you again. Yeah, let's just fix the issue at hand now. Yeah, wipe. Yeah, that makes sense actually. What happened here? Can't change the screen. Huh. Please go. Oh, let me do this. Let me. Oh, yeah. If I switch desktop, I'll lose the record of the share unless I pause the record and then rerun it. Okay, let me just let me pause the record. Yeah, apparently it fixed it, right? Wow. Okay, let's continue. So we arrived to the point that we computed the number of stalls, 3 for the control hazard, which is here. You can either put it at the first of the first instruction, at the beginning of the first instruction, or at the very last. Because technically, this 3, if you come back to L1, would be this, right? After that, you're going to have this. Or if you leave the loop, you're going to have another instructions here. So, and then the remaining, these 5 of 3 are for the read after write. So in total, we had 18 stalls, right? And I was talking about the fact that when you have 8 instructions, 8 IC instruction count, the overall number of cycles, right, would be instruction count plus stalls, number of stalls, which is in this case would be 18. And then we have a 4 because in a 5-stage pipeline, we need 4 cycles to wind down the pipeline. Okay, so always the total number of instructions is going to be number of instruction counts, which is 8 in this case, 4 in the 5-stage pipeline, and number of stalls, which is going to be 30 in this case, right? So normally at the end of each of the section of the question, you're going to be asked to write down some performance evaluations. So the first one would be instruction count, which would be the easiest one. You just count the number of instructions. We had 8 instruction lines, so 8. Number of stalls, you had 6 detected hazard, and each of them without optimization, they would require 3 stalls. Okay, so overall, you're going to have 18 stalls. Then you're asked to compute the CPI. CPI is clock per instruction, so that's pretty easy for you because you have the number of clock cycles. Okay, you compute it, which is, as I mentioned, the number of instructions plus number of stalls plus that 4 because of the pipeline divided by the number of instructions, right? So that shows you the efficiency of your pipeline, right? At this point is 3.75, right? So do you think the higher the better or the lower the better? Which is better? Oh. Why the lower the better? Yeah, it's more efficient. It requires fewer number of cycles, right? So the goal would be, the worst case scenario would be what? The worst case scenario would be, oh, I guess I'm having some issues with this. Yeah, that's the issue. The worst case scenario would be 5, because at worst case, you need to wait for every instruction as if you didn't have any pipeline, right? The best case scenario would be just to have no stalls at all and run everything one after another, but eventually you won't even make it here because you are using a pipeline, so that pipeline requires at least 5, right? 5 cycles. So anyways, you always have this 4 for a pipeline of 5 because you needed at least 1. So instead of 1, you have 5. So that would be at least 4. But if you have like millions of instructions here, this will be super close to 1. Okay, close to 1. All right. So now we understand that the lower the better, and then we can compute throughput. Throughput is the amount of job right? That can be done by the frequency of the processor. So the higher the frequency of the processor, which is the frequency of clock, which was given in your question here, normally either it's going to be given as your clock or in nanosecond, right? You can simply reverse it, and it's going to be your frequency. Okay, so 2 nanoseconds would be, it's like 1/2 nanoseconds, right? And then this one brings back up, and it's going to be positive. So that would be your 500 multiply 10 to the raise of 6, right? What's the purpose of +4 in the denominator? Because are you talking about this? So assuming you have a pipeline, right, without any stalls, right? Assume this one didn't have any of these stalls, right? Everything was perfect, okay? You were just running this pipeline. You have 8 instructions, right? Why it requires 14 cycles, 12 cycles to finish? Why? Because 8 of them would be for this up to here, but we are having a 5-stage pipeline. So each instruction requires 5 stages, right? So if you start the issue in the first stage of the pipeline for the first instruction, when by the time the final instruction finishes, you still have to wind down the remaining 4 of those, okay? That's why even for the case that we didn't have any stalls, you would require 8 plus 4, right? For 8 of them you had to issue, and then you have 4 of them to wind down. And then when you add the stalls, you have the number of stalls added to this. So your 12 would be with the 18 stall here, that would go to up to 30, right? And that's basically what you need to compute. So your 8 instruction counts, 18 stalls, and the CPI would be the overall number of cycles, which is 30 divided by 8, 375. And the throughput would be in MIPS, which is just think about MIPS at 10 to the raise of 6. So that's in research and in books, when we talk about throughput expressed in MIPS, is like mega instructions per second, and mega is 10 to the raise of 6, right? So the throughput would be your frequency of the clock divided by your CPI expressed in MIPS, which is 10 to the raise of 6. So 3.75 multiplied 10 to the raise of 6, which is this CPI MIPS, and that would be your 2 nanosecond processor. And you divide it, and you're going to see 133.3. So this has come from your question statement, which was mentioning that 2 nanosecond is the speed of the processor. The processor clock cycle is 2 nanosecond, right? Each cycle of the processor is 2 nanosecond. So like each one is it's 0 and 1, 2 nanosecond, right? So in order to compute the frequency of that, you need to just reverse the number, and you're going to end up. No, it's just it's a frequency of the processor. I mean, it is actually in a way you're right. At each second, it's kind of go back up and down 500 times multiplied to 10 to the raise of 6, because each of those are 2 nanosecond long. Okay. Sure, you just have to divide this. What is nano? Can anyone mention? Is 10 to the raise of 9, right? So 2 nanoseconds. So 1/2 is half, right? And this nanosecond, in order to make this, you need to bring it 2 i's. So it's going to be 500. So it's like 5, 50, and 500. So you are wasting 3 of these. This is -9, actually. Oh, I wrote it very, very dirty. Let me just again. So it's 1/2 nanosecond, which is 1/2 to the raise of 10 to the minus 1, 9, and then it's going to be 5. This one goes back up. It's going to be positive. It's going to be 9, which is 506. Okay. Yeah. I always confuse that micro, mega, and giga and nano. All right. So that's how we got to 500. Here we used it. So this is 500, and this is the CPI we just computed in MIPS. Okay. So can anyone mention what does this mean? In high level, what does this 133 mean? Yeah, million instructions per second. But what does that number? Oh, I lost my Zoom. Where are you? Yeah. Okay. So what does this 133 mean? So that means that actually from the 500 multiply 10 to the raise of 6, okay, that million, out of that 500, your pipeline is able to utilize 133 of that, right? It's as if exactly that's why you're at the factor of 3.75, which is not very good, because you want to make sure that it's closer to 1, so that if it's closer to 1, you're actually utilizing all of the availability, all of the clock frequency of your CPU, right? So assuming that it would have, in a perfect board, it would have been able to execute 500 megahertz MIPS, right? 500 multiplied 10 to the raise of 6. But because of the way the pipeline goes, we are able to throughput 133 out of that, okay? Yes, yeah. Okay, right. So, so that's the first part. Now, normally we're gonna add gradually some optimizations on top of that. So in the part B, now we're gonna have some optimization. So we're gonna have these 3 optimization. In register file, it is possible to read and write in the same address at the same clock cycle. Remember in our data path before, the first, because of the triggering at edge, right? We were reading and writing in the same cycle, right? So that would make sense that be able to just surpass or alleviate one of the issues we had. Remember here where we were here, right? So this optimization is able to resolve this issue for us, read and write at the same cycle, right? So that's the first optimization. That's what it tells to us. So the first one is telling us that it's possible to read and write at the same address at the same clock cycle, okay? So that's for that. The second one, we have forwarding now. So now, instead of waiting from write back, now for all the instructions except load, I'm able to forward my results from X to X, right? Except load, which is I have to still wait to mem to X, right? Or mem to mem, depending on the scenario, right? So that's what it's telling us. And the third one, program counter calculation for branches has been anticipated in ID. Now we have sort of a branch prediction, either a dynamic or a static one, that tells us, okay, do not wait up to instruction fetch. Do it, go to ID, and then we're going to anticipate the branch prediction at ID. and hopefully we won't miss it. Okay, so we have these 3 optimizations. Now, given these 3 optimizations, let's see what are the issues now. Okay, we have started from 18 cycles of stalls. Now let's see if we can bring down some of those issues. Okay, now instead of here going from write back to ID, now I have forwarding. However, the instruction is load, right? LD or LW we wrote here. So I can forward the results from mem now, right? So if I forward the results from mem, I've already passed the issue, right, to the ID now. However, the issue here is I don't have to wait now for 3 stalls. Still, I have to pay a price to some stalls, and we're gonna figure it out how many. Okay, so that would be still my first issue, but we have alleviated a little bit to some point. Okay, the same goes with this one. Now I don't have to wait up to write back. I can just forward the results from mem to the previous. So the mem of this is gonna forward the results to the previous register. So when it's as its mem instruction, the next instruction comes. The add I is that execution instruction, right? So it will be forwarded to this, and we can use it. Still, we have to adjust it with some stalls, but it won't be 3, right? Now, if you go back down here, you're gonna see that by forwarding, we might be able to resolve the issue with add I5 and also store 5. We're gonna see it later, okay? And then we might be able to get away at least with some fewer stalls for the branch prediction, because now we are predicting, anticipating at ID, okay? So let's see what would be the outcome of this. So if you actually, in exam, you normally have to just write this and provide the forwarding path. You don't have to write the stalls here, because we don't know how many stalls it would take, and it's going to be a mess if you write the whole table. So normally you don't you're not going to give an all this table. You just have to write down the forwarding path and write down the actual path that was used. Okay, and later on you have to showcase the number of stalls. But in reality, what it happens here is, instead of going to ID, right, and from write back, now we are saving 2 more stalls out of 3. So with just 1 stall, we are able to forward the result of this to the next instruction. That is X, okay? So just 1 no operation would be enough. 1 nope would be fine. 1 bubble would be fine for this. The same goes with this one. This is at memory stage with 1 nope, with 1 bubble. This will arrive to the X, and then we can forward the results, right? That's why we have a mem to X, a mem to X $4.2 forwarding path, another mem to X $4.3 path. Okay, you see that as we anticipated before, we are already at X, so right away it comes at X, and we can read and write at the same time. And this one can right away forward the results to the add now. So not only we can save 2 stalls here, we can completely save all the stalls that happened before without any optimizations now. We can just forward them right away to the next one. And not only this one, after add, we're gonna forward it right to store, okay? So this forwarding path is very useful for us. So we're gonna have a mem to X, so these 2 are for load. That's why we have to wait up to mem. The rest of the instructions are X, because they are non-load. They are add or store, okay? The results are available at the end of the execution cycle. We don't need to wait furthermore, because the last 2 cycles would be the same results. Nothing will change. So we can completely forward it from X to X and X. So that would be the XX of $3 here, and this one would be XX of $5, because we're storing it, okay? So here, so far so good, okay? With just 2 stalls, we arrive at this point. It's pretty good. We didn't have any issue for the add-I previously. However, in order to compare the result of these two, that would be a read after write, right? And the earliest time we can get to know the result of this is at X, right? And the load is anticipating to have it at ID because we have an branch prediction, right? So from X to ID, we can forward the results. However, we need one stall here, okay? And finally, in order to decide what the outcome of the branch comes, right? We need to have another one, another stalls here, right at the start. Okay. So summing up all together, what we're going to have is now one stall for control hazard. We can write it either at the beginning or here. That would be the same, right? In blue, that's the control hazard, CNTR. And we only have 1 and 2 for the first and third load, right? And just 1 for the result of this for the branch, okay? Now you see we have saved so many stalls with these 3 optimizations. We had 8 instruction counts. We are having only 4 stalls. And that would lower our CPI a lot. So starting from 3.25 or 3.75, I'm not sure. We are at 2 now. It's pretty close to 1, and it's a good CPI. And you see, out of our 500 MIPS, like the frequency of 500 megahertz of the CPU, we are able to use 250 out of that because the CPI of the system is 2. So we are almost utilizing half of the upper bound of our CPU, okay? By this pipeline, we are executing at a very good pace because of these optimizations. Is it clear so far? Any questions?
Why we only have 4 star in this chart since we have 6 star in that last picture?
Yeah, so 2 of those that we completely resolved were these paths. We were able to put XXX of $3 and XX of $5, and these 2 resolve 2 of the issues at the same time because we can. So the optimization tells us it's possible to read and write at the same address, right? Because we know at edge we can trigger read and write, right? It's the convention of the clock. So if it arrives at the same cycle, the first, theoretically we're going to call it at the first half of the cycle we can read, and then the second half we can write it. And a forwarding path allows us to just forward it from X to X, okay? So these 2, we saved 2 of those, 6 and 4 left. And those remaining 4, instead of 3, were 1. So that's why these 2 resolved. And then we have only 1 for control because we are having a branch predictor. And these 2 for the forwarding. The rest with the forwarding got resolved automatically. And then this one is another read after write because we have to understand the value of $4. Okay?
Okay.
All right. So now you see that from 3.75 and 133 throughput, we arrive to the point of 2 now and 250, which is not bad. Okay. Now let's see if we can go any further than that. Okay. So on this third part, instead of a dynamic branch predictor, okay, that or just a hardware branch predictor that anticipate always at ID, now we have a static branch predictor that always does something, and that something is provided to us by the exam, by the statement. So beside the previous optimization, we assume to introduce a static branch prediction for backward branches, okay? And the case of the static branch is backward branches always taken. So backward branches taken. Okay, so it doesn't matter for this guy. Whatever happens, it's going to take the backward branch. Okay, so that's a static branch. It has been statically set, and perhaps it's been built in. Assume it's been built in the hardware. So anytime we hit the branch, it's going to go backward. So the backward branch is taken. Okay. So that would solve our control hazard technically, because when we are here, although we were anticipating an ID for the next stage, but we know what to go. We know where to go here. So right away we can fetch an ID the second or the n+1 or i+1 iteration of the loop, right? So this branch predictor, which is the static one, because it's always backward taken, it's going to resolve at least the control hazard we had. And we can see it here that because of the load issue for the mem to x, we have the same one installed there. This one also has the one installed there. This xx had no issue. They were resolving the problem. Here, in order to compare the value of $4 to $7, technically we are wasting another no operation or one bubble anyways, right? But when it comes to this branch, it says I don't care. I'm just gonna go back to L1. Okay, the backward will be taken. Yeah, it's been statically set on my branch predictor. I'm gonna come back. So that's why here, all good. We know what to issue, what to fetch, and what to decode. Okay, so that's why we save one more stall for the control hazard. So now control hazard is gone, right? None. Now, if you add up the previous stalls we accumulated, so it's going to be only 3 now. One for the first load, and one for the second load, and one for the outcome of the iterator to check with this. Now, you have only IC of 8 and number of stalls only 3. So now you see we are even lower than 2 now, 1.875, which is technically out of 500, we are utilizing 266 of the CPU clock. In modern world, let me just add this, that if you have a static branch predictor that you know you're going to come back, you might be able to get away with this by reordering, and you might even don't have to pay the price of this. But for the sake of this question, you just have to follow the rules, right? We need the value of this, so we have to pay the price for that. But in real world, there are ways to get away with this. All right, so now we have 3 stalls, and the CPI is 1785. Any questions? All good? Give me a feedback in chat. Okay. All right. So let's see if we can do anything else. I mean, we started from 3.75 and we are at 1.875, which is not bad. Let's see if we can play around with the code to optimize it more in the pipeline. Now, scheduling or reordering, okay? Let's see if we can reschedule the code or play around with reordering it manually, okay? Now, that was the old order or schedule. Okay. Now, remember in the other lecture we were talking about reordering or rescheduling the instructions. We thought that, okay, let's just put these two as further as possible, because right after we load, and this should be D, but this should be D, okay? Right after we load $2, we are adding $2. So why just give it a little bit of slack to just these two be as further as possible, so we get away with at least a nope or a bubble. And since it doesn't change or it doesn't affect the execution of the loop, right? We are able to afford that. If we manually reorder this, we're going to put these two loads next to each other, okay? So as if that was the best base A of I, and this one for the B, right? And then we can also reorder to the way that this iterator, remember this was the I++, right? It doesn't matter if you just I++ it after the increment of this and the addition of both and here. Why not we can just have it here and give these two some space, right? So that this $2 and $3 don't get messed up again when we add them up, right? In the past, it used to be here, right? That was the I++. It didn't change the course of the execution, so why not just bring it up here, okay? It makes sense. So by bringing this up, now this have enough of cycles to complete its execution. So when we do the add I for $2 and $3, they are far away. So like this one has like 3 instructions away from this, and then you're gonna have $3, which is again 3 instructions from its previous usage, right? So we got away from this. And finally, we need to add this. And you remember we were having forwarding, so X to X will allow us to forward the results right away, okay? And we're gonna reach up to the point of the branch, and we had the static branch built in. I'm gonna take backward always. In this case, it's gonna work, right? And finally, by adding another hardware, which is called branch delay slot, you can do the branch, right? You can estimate the final address of the branch using that PC relative addressing, and then issue another instruction for delayed instruction after the branch. I mean, in exam, you're not gonna ask for this type of question, but this is just for your information, how we're gonna, in modern world, how we're gonna play around and use more hardware and more advanced technology to just get away with all those bubbles. Sometimes we try to fix them all, but sometimes it won't be the case. This is a small loop. It was doable, right? So what by reordering these, we load them both after each other, and then we insert that iterator incrementation. So like the I++ here, give us some distance between these two, and then we add $2, $3, and then we add, we use the forwarding path. We play around with the branch, and then we store it finally. And you see that by this rescheduling, we are actually able to resolve all of the stalls. Now there's nothing left for us as hazards. So we rescheduled these 8 instructions, right? And all good here. You see, we have the forwarding from mem to x, which is fine. We have the forwarding of x to x, which is fine. Another x to x, which is fine. Still, you have to write down the forwarding. And here, we play around with the delayed branch, and that would resolve this x to id as well, right? So actually, we have the same old instructions with no stall. And you see the instruction, the CPI arrived to the point of 1.5, which is the optimal case for an 8 instruction count pipeline of 5, right? If we had like 800,000 instructions, that would be pretty close to 1. But since we have only 8 instructions, we are still paying the price of 4, and this 4 sounds a lot in 8. That's why it hires from 1 to 1.5, right? And right, let me just get this. And here, sometimes they use this method. They call it asymptotic throughput, and this asymptotic throughput is just a limit on CPI without consideration of that 4. That's why we don't consider 4 here. But just in exam, you don't get asked for the asymptotic CPI, okay? You have to use the same old throughput expressed in MIPS, which is going to be your frequency of your clock divided by the CPI in MIPS, okay? So you just divide this to this, and you're going to arrive to, let me just, up to 333. So out of your 500, you're able to utilize a majority of that, okay? And that's a good sign for us. Any questions so far? So this would be a type of questions you're going to get asked in final. And as you see, it's pretty easy. You just have to analyze different things that you've been taught in chapter 4. There are no strange or special cases. You just have to understand when we need stalls, if it's 3, if it's 1, if it's 0, if we can play around, if we can use the forwarding or branch prediction, and we have to write down the things that we've done here in the forwarding. Or if you were asked that, okay, write the branch condition or branch status, you just have to write here branch always not taken, or forward taken, backward taken. You can just write whatever the information was here, okay? Any questions? All right, so I guess that will sums up our chapter 4. I guess it's pretty late to start chapter 5, so I'm just gonna stop here, and next week we're gonna talk about chapter 5. Sure. Yeah.
So I was wondering, is it possible if we can split or actually shift the weight onto the lab rather than the midterm?
Actually, by splitting the weight, I was talking about the splitting overall grade so far, so labs and midterms. So by now, by both of the labs, like the lab tomorrow and then the next week, you're gonna complete 62% of the course so far. You will be completing 62%. So for the remaining 38%, I was having a poll, which I'm gonna put it up again in Moodle so everyone can access and vote. But the upper one would be the same original case, which was 38%, and the lower one would be something lower, either 30% or 20%. I don't think 10% would be a viable case because it's final, right? It has to mean something. So maybe I'm just going to put up 38, 30, and 20 only, and then see what the guys are going for. Yeah, future labs will be each graded as 4, right? Just like before. 4 for M and 4 for N, right? Yeah.
But my question is, if we shift the weight from the final, would it be possible to shift it on the labs only?
Why just the labs? You've done midterm as well.
Yeah, but some people did bad on the midterm.
I guess the average of the midterm was around 19, which was pretty good. So everyone, I mean, whoever got more than 19, he will benefit from shifting the weight actually.
Mm-hmm.
Yeah.
Okay.
Yeah. Any other questions? So after this, I'm just gonna upload the video on YouTube and send you the link.
But I have a question. But
Sure.
in terms of like the same thing, like in terms of shifting the percentage, like although we shift, like can we just shift like the majority of that percentage to the labs and then a little bit on the midterm?
I mean, if you want to go with that path, there are so many different combination of shifting, and I just want to don't enter that path because it's a limitless end, right? Like somebody was
Okay.
like, can you shift it more in lab A, or like 2% to B, and then that's going to be a endless path. So I would suggest not to go with that path. Either we're going to go with the same old technique, 38% final, or something between 38% to 20%. Then I'm gonna just amplify the first 60%. That's all. And it's just because you are doing it online, and perhaps someone might get more stress, or they might feel it's not fair because someone might just not be able to perform as well. So that's why I'm doing this. If the majority decides they want to keep the 38%, I'm fine with that.
And I have a question. So for the final, when it's online, how's it gonna be? So is it?
Yeah, it's I still haven't figured out the method, but the questions would be the same thing that you had in midterm, so the same style, and we just have to find a way to find a proper submission for that. so that it's going to be fair. I want to make sure the process is uniform and fair, so that everyone has the same fairness. So that's the most important thing for me now.
Maybe it can be a multiple choice on Moodle.
I guess based on the regulations, I'm not able to ask more than certain percentage of the overall grade in multiple choices. So I'd rather avoid that.
Professor?
Yeah.
How will we be able to write our answers as long as it's online? Are we going to write it on a paper, then take a photo and upload it, or?
For final?
Yeah.
I guess let's talk about finals like 1 week before, because still there are so many unknowns and it's like a month away. You never know what's going to happen. Let's just focus on your lab tomorrow, guys, or on Wednesday.
Okay.
So chapter 4. Yeah, for chapter 4, you might just follow the slides that I shared today and previous week, and the video that I just recorded, and I'll put up later in YouTube. Because in previous semester we taught a little bit more, but yeah, I try to just conform with the current circumstance. So I removed some of the slides, especially for exception handling, so they are outside the scope of the final exam. So whatever that is on the slide that I already uploaded in Moodle, that would be on your final.
Question, please.
Yeah.
Why can't we have 90 minutes for our labs?
Because now it's online. It's not even yeah. I want to give you. I want to just raise your blood pressure a little bit.
Will the online labs be proctored?
How can we do that?
Where you have someone watching, you have
online?
to have a webcam on?
Like,
yeah. I mean, there's services for it, but like,
I don't think nothing can be perfect online. I mean, even you are just fixed into looking at camera, there's no way that is completely fair. I mean, there are always ways to just do otherwise, right?
And it's
there's no way to
privacy.
guarantee that. I don't think it's and it's proven. Yep. No, not 80. 60 minutes, that would be all. Let me stop share. Questions? Yes, I will send another announcement in Moodle for another poll, because this poll was kind of not democratic poll, and you were only 47 people. We need more than 50% of the class to poll, okay? So tomorrow and Wednesday, just go online, find in the lab section of Moodle, find your question. If you download the question, you must answer it, otherwise you're gonna get 0. You can't just see the questions and don't answer and then come back to the next lecture, come back to the next lab section. This is the 3rd time I mentioned this. And use web submit to submit your pre-lab up to tomorrow before the lab test, and then in the lab time, you have 60 minutes to submit your lab to the lab test folder, which I'm gonna show it on the PDF. It's gonna be either M01, M02, or M03, depending on the section. I'm gonna post the questions 5 minutes before the lab test starts, and I'm gonna post an announcement so you have enough of time to check it, okay? But just look for that web page right at your lab test time. If it's 9:30 to 12:30, your lab test would have been started at 11, so just look for it at 10:55. It's gonna show up, okay? Or if you had lab from 7 to 10, it would have started at 8:30, so it's gonna be there at 8:30, right at your lab test time, as before.
okay. Regarding the pre-labs, I had one of the pre-labs where I forgot to submit my pre-lab for the lab. Will I get marks deducted, or how is that going to work?
Say that again. You had a pre-lab, you didn't submit, or you
I did the lab, but I don't think I submitted the pre-lab for one. Am I just going to get?
Send me an email and submit the pre-lab, so I mark that.
Oh, okay.
Yeah, I guess the submissions for pre-lab is open, but I can see what time you submitted. But send me an email so I'll make sure I don't remove that. Okay.
Okay.
Okay. Other questions? Pre-labs are an entrance to get graded for your labs, okay? Just like before. If I don't see a pre-lab for a lab, you're gonna get 0. Right? Other questions? Lab L mark, yes. Yeah, they are partially out. I'm waiting for other TAs. Yeah. You can check your Moodle in a few days. It's gonna be up. No, the difficulty would be the same. I mean, we were lucky. Nothing really changed in this course for us, except the fact that you have the freedom to just lie down at your comfort of your home and then drink a coffee and do your lab. Okay. All right. If there are no other questions, let's wrap up the class. Are there any questions?
There's no way at all to make it 90 minutes.
No, 90 minutes would be a long time for an online test. No.
Okay.
Yeah. I'm sure you do well in 60 minutes. Because I've seen in your previous labs, the majority of submissions has been done in the first 30, 35 minutes. So you're fine. You're going to have extra time.
Okay, thank you.
Yeah. Okay, guys. So make sure to poll tonight when you see my announcement. And I'm going to put up this video online so you can have a look at it later. All right. Thanks a lot. Hopefully we can conclude the semester as before, and stay safe and take care of yourself. Okay, have a good night.